Hello and welcome, Mason Storm DIY Audio here. In this video series we're looking at making some hi-fi speakers. This video we will be looking at selecting mid-range speakers and tweeters, as well as the basics of crossover design. So here we have our driver from the first video, our peerless subwoofer driver that we will be using as a woofer in our hi-fi system. And if we look at our frequency response here, we can see that it starts to dip before it starts to break out, probably around 600 Hertz. So around this point, we're going to want to install another driver that will extend it further till we need another driver to take it all the way up to 20 kilohertz, the extent of the human hearing range. The second driver will be a mid-range driver, and the third driver will be what is known as a tweeter, or the higher frequency driver. Speaker crossovers are typically not an iron gate transfer from one to another. Typically there's some form of slope involved. And for this reason, the mid-range driver, even if it's crossed over to the woofer, it can actually assist in frequencies below the crossover point, increasing the tolerance for the potential loudspeaker system, creating a more flat and level sound. This picture is from the audio crossover section on the Wikipedia page, and it shows how two lines can be summed to a greater value than the initial. When we're going to be doing crossover design, we're not going to necessarily cross things over in an even way like this. We can use different slopes from one to the other to create summing in different portions to give us more control over the output value. Having different slopes will allow for a greater degree of fine-tuning when it comes to crossover design. This image shows the two basic types of crossover filters as well. We have our low-pass filter, which allows low frequencies to pass but blocks high frequencies. We have our high-pass filter, which allows high frequencies to pass but blocks low frequencies. So for selecting our mid-range and tweeter for this system, we're going to want drivers at least as sensitive as the woofer, probably around 88, 89 dB, or a little bit more, because it's possible to lower the sensitivity on a driver, but it is not possible to increase it. Some builds for speakers like to use dual mid-range drivers, and this is a way that can increase the sensitivity. Doubling the drivers is the same as increasing the driver sensitivity by 3 decibels. When selecting a mid-range, I like to select one that has at least 1 octave lower resonance frequency than the low point on our crossover. Let's say 500 is the crossover, so we would want something with an FS of 250 or lower. Having an octave away on the mid-range driver should be enough to protect it from destruction. The same will apply to the tweeter as well, but a lot of manufacturers of loudspeakers like to use more than 1 octave because it makes the tweeter more resilient and thus lowering the amount of claims as far as warranty goes. I've actually looked around and already decided on a couple drivers for this system. The goal is to keep it under $500, 500 Canadian, so about 400 American. So I'll show you what we have so far. This is the woofer. It's about 50 bucks. Mid-range $30, and our tweeter is 14. Let's take a look at the data sheet for our mid-range. So here we go. We have ourselves a 4-inch aluminum cone woofer driver that we'll be using as our mid-range. And if we look down here at our resonance frequency, 82, it's right in the range we want, as in less than 250. And here's our frequency response. First thing you'll notice, it's a little bit low on the sensitivity. Probably should have got something a little bit more sensitive. Probably could have got something a little bit flatter at this portion here. But when I was playing around with the crossover design software, I found that using an air coil of lighter gauge on the woofer, the sensitivity dropped a bit, so this actually worked out pretty good. May look very jaggy in this area, especially with the red line, but 60-degree off axis is kind of a big amount. A lot of other speaker manufacturers, they have 15, 30, 45. They don't usually have the 60-degree, just depends. But 60-degree, that's a pretty far off axis, so I'm okay with that. But if we look at the pink line and the black line, they're fairly consistent for the most part, kind of in the band that we plan to use it on. So it should work out pretty good. This driver would probably actually be good in a nice two-way system with a very small enclosure. I haven't actually run it on WinISD, but that might be another way that this can be done. Oh yeah, and it's also a 8 ohm speaker, kind of matching the first driver. Here we have our tweeter. We'll zoom in here. That's a 4 ohm driver. Go down to our technical specs here. It's a transducer size, 3/4 of an inch, with a resonance frequency of 1050. Something to note here is for the sensitivity, we got the 2.83 volts at 1 meter, and then we have the 1 watt at 1 meter. If this was an 8 ohm speaker, those would be the same value, because applying 2.83 volts to 8 ohms gives 1 watt. But in order to show the difference between a 4 ohm load and an 8 ohm load, they also have the 1 watt 1 meter, which voltage wise will be a bit lower. Then scrolling down to the chart, we see that even this driver goes into beaming. 0.75 inches is not a small enough size to prevent beaming over the entire audio spectrum. The transducer would have to actually be quite a bit smaller to do that. But the issue comes that as the driver gets smaller, that the power handling goes down. And due to the wide frequency we'll be using this in, that kind of becomes impractical. Other tweeter types have better or worse beaming tendencies, and compression drivers in horn-loaded systems can have different dispersions as well, and it's just a matter of kind of tailoring it. But with the way that this rolls off here, mainly focusing on our 30-degree, it's still better than AM radio. AM radio rolls off most high frequencies. I believe it's 7,000 hertz that it starts to kind of roll off, but in this case, listening to the speaker will sound the best when directly in front of it, and we'll have a little bit of roll off in the high frequency when a little bit off axis. That's another point of note, that human hearing in adults starts to reduce from 20 kilohertz, so it's usually not as big of a deal. It's best to try to do everything you can, but typically on high frequencies, it's much more difficult to prevent the roll-off. And a lot of the idea in speaker design, especially floor towers, is keeping the tweeter at ear level to ensure the maximum amount of sound is on axis. Because even moving up or down can take the listener off the axial plane and reduce sound quality. So having the speaker at ear level, as far as the tweeter goes, is one of the fundamentals. This hump over here may look really bad, but with the way we're going to be crossing this over, it'll be a reduction over a frequency band. So we'll have an octave. So from 2000 to 1000, we subtract 6 or 12 dB, and that will kind of give us our nice roll off on there. And as far as the high frequency goes on here, probably going to lower that a little bit so it's more in line with being flat, but probably straddle it a little bit above the true reference line, and that will give additional reinforcement to the off-axis response, making it so that even sitting off-axis, the reduction isn't as great. By straddling the line, like the main reference audio line between the two, will give a much better listening experience for everyone by not totally focusing on one particular point. When it comes to actually designing the crossovers, it's a electrical process, and I think some of the key terms for this or components need to be understood, at least to some degree. There are three main electrical devices that are typically used in the crossover design: the resistor, the inductor, and the capacitor. Here we have the symbols for the resistor. I typically use the squiggly line version on the top more often, but the other is totally legitimate as well. Here we have the Wikipedia page on resistors, and we see that resistors reduce the current flow in a given system. There's two main properties to the resistors. There's the amount of resistance that it has, measured in ohms, and then there's the ability for power handling, which is the amount of watts that a resistor can handle. The amount of power that the resistor needs to be able to take will vary depending on the power requirements of the given system. But typically resistors are cheap, so just selecting a 10-watt resistor is usually good enough. And if you're doing a system that's several hundred watts, it may be worth running a simulation or solving the circuit using the Kirchhoff current law and Kirchhoff voltage law rules, or selecting an oversized resistor and not worrying about it. Here we have the inductor symbol on the inductor Wikipedia page. Definitely worth a read through. Inductors are measured in henries, and they're similar to resistors in that they resist the flow of electrons, but are different in that they are frequency dependent. If you take an inductor and you increase the frequency of the system, the amount of current will be reduced. This is what makes it such a good filtering device. 1 Henry is actually a pretty big size for an inductor as far as crossover design goes. Usually we use millihenries. Inductors are typically made by wrapping wire around a core, as we can see in our different examples over here. But they can also be made without having a core inside them. When using a core in an audio crossover, it can lead to saturation under certain situations, and when a core gets saturated or too much current goes through the inductor, its inductance will actually reduce, and then it will lose the benefit of having the core and act as a straight wire. And this can cause all kinds of distortion in an audio system. So usually it's better to use an air core inductor because they cannot saturate and will remain the same over any load. However, without having a core, it takes more turns of wire to reach a given level of inductance. As such, the resistance in the system increases because it takes a very long length of wire, and wire over a longer period, longer length, will add some level of resistance. This can be countered by using thicker gauges of wire. However, this can become very expensive, and inductors can be the most expensive crossover parts in a given system. Here we have the symbols of our capacitors. In crossover design, we use AC circuits, so we cannot use a polarized capacitor. We have to use a non-polarized one that will work in either direction. So this is the symbol that we'll see on our circuit diagrams when we design our crossovers. Here's our Wikipedia page on the capacitor. Feel free to read it at some point in time. Just know that capacitors are measured in their capacitance, which in audio crossover terms is typically microfarad, which is the weird little U symbol. And there are many types of capacitors as far as manufacturing technology goes, and depending on the type, the price can vary quite a bit, but typically a bipolar, non-polarized electrolytic is quite cheap, but they only have a limited shelf life of like 20 years, whereas other types like propylene and metal, polymer, whatever, last for quite a bit longer. As the value of the capacitor changes, the amount of low frequencies cut off change as well. Increasing a capacitor's capacitance will allow it to pass more low frequencies than a smaller value one. That's probably the bare minimum we can do for looking at passives. For the most part, we'll just be using them. We don't have to necessarily know the innards of how they're made or what exactly they do. Just that certain values in our given system will produce desired results. So this is what a schematic will eventually look like. We will have 3 of these for our speaker, one for the woofer, one for the midrange, one for the tweeter. Not every component that's shown on here will be populated, only some of them will be. But the thing that's important right now is just to know which each symbol is. This is an inductor, this is a resistor, that's a capacitor. And knowing that, we'll be able to move forward with the crossover design. In the next video, we'll actually design the crossover for this speaker and explore some of the ways that crossovers can be designed. It should pick up and be more interesting. Till next time, like, comment, and subscribe.